At the very center of our galaxy lies a region so dense that 4 million suns are compressed into a single invisible point. It does not emit light, yet its gravity controls the orbits of hundreds of billions of stars, including the sun we orbit. This object is known as Sagittarius A*A, supermassive black hole confirmed through decades of observation and precise measurement. Tonight, we'll follow the evidence from radio signals first detected in 1932 to the most recent Event Horizon Telescope data to understand what truly exists in that hidden core. Before we step into the silence at our galaxy's core, I'd like to ask just one gentle favor. If you leave a soft like or quietly press subscribe, it would mean more than I can say. It tells me these calm stories, whispered between science and sleep, are still finding their way to kind minds like yours. Your quiet support keeps this little world of curiosity breathing, and I'm truly grateful you're here sharing this moment among the stars. Now let's begin part 1. What exactly is hiding at the center of our galaxy? At the center of the Milky Way sits a mass about 4.1 million times the Sun, packed into a region smaller than Mercury's orbit. Invisible, compact, and in control of the galaxy's motion. It does not shine, yet everything near it obeys its pull. We found it by following a pattern, not a picture. In 1932, radio engineer Carl Jansky built a rotating antenna at Bell Telephone Laboratories to hunt down the source of static that ruined long-distance calls. The device looked simple: wooden beams, metal tubing, wheels, but it could sweep the sky and measure faint radio noise. Jansky logged thunderstorms, he logged local interference, and then he noticed a signal that repeated every 23 hours 56 minutes. A sidereal day, the time it takes Earth to face the same stars again. That 4-minute difference from the solar day told him the source wasn't the Sun or Earth. It was coming from space. Tracing the direction put the source in Sagittarius toward the Milky Way's dense core. The galaxy was broadcasting in radio. Jansky published his result in 1933. His antenna was dismantled. Radio astronomy paused, but the clue was on paper waiting. By the 1970s, radio arrays had matured. Using interferometry, linking antennas far apart to act as one, Bruce Ballack and Robert Brown pinpointed a remarkably compact radio source at the very center of the Milky Way. They called it Sagittarius A*. The asterisk, borrowed from atomic notation for an excited state, flagged something unusual and energetic. Knowing it was compact wasn't enough. We needed mass and size. Visible light can't pierce the dust toward the People Galactic Center, but infrared light can. In the 1990s, two teams, Reinhard Genzel, Max Planck Institute for Extraterrestrial Physics, and Andrea Gzi, UCLA, used adaptive optics on the Very Large Telescope in Keck to watch individual stars crowding the core. One star S2 traced an ellipse that closed every 16 years. Near closest approach, S2 tore past the center at about 7,600 kilometers per second, nearly 3% of light speed. From the orbit, the mass enclosed had to be about 4.1 million solar masses confined within a volume smaller than the solar system. A cluster of normal stars would collapse or drift apart. A ball of dark matter would not stay that tight or match the observed speeds. The simplest testable explanation under general relativity is a supermassive black hole. The teams measured for decades, refining positions millarcs by millioxic. Their results agreed and matched Einstein's predictions for strong gravity to high precision. In 2020, Genzel and Gzi received the Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. Next came the request no picture had ever answered. Could we see its shadow? The Event Horizon Telescope, EHT, joined 8 observatories across the Earth in 2017, synchronizing them with atomic clocks to create an effective dish as large as the planet, a method called very long baseline interferometry. They recorded petabytes of data and flew hard drives to central facilities for correlation and reconstruction. Sagittarius A times changes on minute time scales. Its mass is smaller than M87 asterisk, so its plasma whirls faster. so the team also had to solve the problem of imaging a moving target. In May 2022, they released an image, a ring of radio emissions surrounding a dark interior. The expected shadow cast by light bending around the black hole's event horizon. The ring's diameter, about 12 million kilometers, matched predictions for a to 4 million solar mass black hole to within roughly 10%. As the collaboration summarized, the appearance of Sagittarius at times is remarkably consistent with the predictions of general relativity. So we have three independent lines that fit together. 1. A compact radio source at the exact dynamical center. 2. Stellar orbits S2 and others, demanding a massive tiny region. And 3. A horizon-scale image consistent with a black hole shadow. Yet Sagittarius at times is not a bright, roaring engine. It is in a low accretion state. Between active feeding cycles, supermassive black holes generally pass through phases: quiet, then active, then quiet again. Our galactic center is currently quiet. Even so, space telescopes catch brief X-ray and infrared flares that last minutes. Instruments like Chandra, XMM, Newton, KEK, and the VT have recorded these spikes. The team leading explanation is magnetic reconnection in hot plasma near the event horizon. Magnetic loops twist, snap, and release energy. Some matter falls inward, some is flung away. There is another large-scale clue that the center was more active in the past. The Fermi bubble's gamma-ray maps reveal two lows stretching about 2,500 light-years above and below the galactic plane. Their size and energy suggest an outburst from the center a few million years ago, possibly tied to rapid feeding or a jet event. Today's calm likely follows that earlier bright phase. The same object, different moment in its cycle. Quiet does not mean inert. The central environment compresses gas clouds. Under the right conditions, that compression helps form new stars in the inner few parsecs. The same gravity that pulls matter apart sets densities high enough for collapse elsewhere. Destruction and formation occur side by side. A closed loop that regulates the cause. Supply of gas. Two scale checks help anchor all of this. First, the Sun orbits the galactic center at roughly 230 kilometers per second, taking about 230 million years to complete one revolution. We are passengers on that long path. Second, the Milky Way is only one among hundreds of billions of galaxies we can observe. Most large galaxies seem to host a central supermassive black hole. Our case is special not because it's unique, but because it's nearby, allowing measurements that are difficult elsewhere. And there is the time factor. The light we detect from the galactic center took tens of thousands of years to reach us. Light from distant galaxies took millions to billions of years. Every observation is a look back, a record of how things were when the photons started their journey. When you see a picture of the Milky Way center, you are seeing its past state, not its present moment. What about the idea that black holes explode? Here the wording matters. According to quantum theory, black holes should emit Hawking radiation and slowly lose mass. Very small black holes would end in a rapid final outburst. For supermassive black holes like Sagittarius A*, the evaporation time is far longer than the age of the universe, effectively unreachable on human or stellar timescales. In practical terms, our galactic center will not end in an explosion we could witness. Its changes are governed by accretion cycles, stellar interactions, and galaxy-scale dynamics. A few historical threads, tied simply, show how evidence accumulated. JWST, sidereal signal 193233, the first radio detection pointing to the galactic center. Ballack and Brown 1974. A compact radio source named Sagittarius A*. Infrared astrometry from the 1990s to the 2010s. Orbits of S2 and others prove a to 4.1 million solar mass object in a tiny volume. Results match 22. General relativity. EHT image 2022. Horizon scale structure consistent with a black hole shadow of the expected size. Alongside these milestones, instruments filled in the environment. Chandra and XMM Newton for X-rays, ALMA 4 mm emission and polarization, KEK VLT for infrared orbits and flares, and Fermi for gamma ray structures. Each added an independent piece. Together, they describe a single coherent center. 3 practical comparisons keep the picture clear and approachable. Speed S2 at pericenter to 7,600 kilometers per second. Moves about 20 times faster than Earth's orbital speed 30 kilometers per second. Size. The EHT ring to 12 million kilometers across is roughly 30 times the Earth. Moon distance to 384,400 kilometers. Distance we are to 26,000 light-years from the center blank. A photon leaving there when the last ice sheets covered parts of Earth is only now arriving. Why present this in a slow, steady way? Because the pattern matters. First the repeating radio day, then the compact source, then the tracked orbits, then the horizon scale image. Each step answers a specific question and leaves a sharper one behind. Remaining questions are clear and testable. Spin. How fast does Sagittarius at times rotate, and how does spin shape the inner accretion flow? Magnetic structure. How do magnetic fields thread the plasma near the horizon, and which reconnection geometries power the flares? Feeding cycles. What external triggers gas inflow, disrupted stars, cloud encounters, switch the core between quiet and active phases? Star formation balance. Under what pressures and turbulence does gas in the inner parax flip from being heated to forming new stars? Answering these will require the instruments already moving into place. JWST to watch the dust-embedded infrared scene with higher sensitivity. The next generation EHT to sharpen resolution and track time variability, and related polarimeters to map magnetic fields and X-rays, and farther ahead LISA to listen for low-frequency gravitational waves from massive and spirals that test gravity near the core. Everything you've heard so far is observable, measurable, repeatable. A rotating antenna isolates a sidereal signal. Linked dishes resolve a compact source. Infrared cameras track stellar ellipses and computer mass. A planet-sized interferometer outlines a shadow where light cannot escape. Taken together they describe one object, Sagittarius A**. We began with a fact. We end with the next test. If all this evidence points to a supermassive black hole, which single observation most decisively closes the door on every alternative? And how exactly was that measurement made? That's where the trail leads in part 2. How did we prove it's a black hole? For decades, the center of the Milky Way was a mystery wrapped in light that we couldn't see. Every telescope that tried to look there met the same obstacle: a curtain of interstellar dust so dense that visible light could not pass through. The region was silent to our eyes, but alive in other wavelengths, whispering in radio and X-ray tones. We knew something massive lurked there, but proving that it was a black hole and not some other exotic object would take a generation of persistence, precision, and patience. To understand what we did, imagine trying to weigh an invisible mountain by watching the way birds fly around it. That in essence is how astronomers uncovered the truth about Sagittarius A**. In the 1990s, a new era of infrared astronomy began. Telescopes like the Very Large Telescope in Chile and the KEK Observatory in Hawaii were fitted with adaptive optics systems that used lasers and deformable mirrors to cancel the blurring effects of Earth's atmosphere in real time. For the first time, we could see the galactic center in sharp detail through infrared light, wavelengths long enough to pierce the cosmic dust. What those observations revealed changed astronomy forever. At the heart of the Milky Way, a small group of stars were orbiting something that emitted no light at all. They moved fast, faster than any stars ever recorded, and all of them circled the same invisible point. 2 teams led the effort, one by Reinhard Gendel at the Max Planck Institute for Extraterrestrial Physics in Germany, the other by Andrea Gz at the University of California, Los Angeles. Each group worked independently using different telescopes and analysis methods, but they shared one goal: to chart the precise orbits of these stars over years, even decades, to calculate what kind of mass could control them. Among those stars, one became the key to everything. It's a young hot star about 15 times the mass of the Sun, and its orbit around the center of the galaxy takes roughly 16 years. When it reaches its closest point to Sagittarius A*, it travels at a speed of about 7,600 kilometers per second, almost 3% of the speed of light. At that moment, space-time itself stretches and curves around it. To measure S2's motion, astronomers recorded its position night after night, year after year, plotting its path across the sky with sub-pixel accuracy. Every shift in its velocity told them something about the gravitational field it moved through. By applying Newton's laws for motion and then correcting for the effects predicted by Einstein's general relativity, they could calculate the total mass of the unseen object. The result was astonishingly consistent across both research teams. The gravitational source contained about 4.1 million times the press mass of the Sun compressed into a region smaller than the orbit of Mercury. Nothing else in physics fits the description except a supermassive black hole. A cluster of stars could not stay that compact without tearing itself apart. A ball of dark matter would not exert gravity strong enough to accelerate S2 to such extreme speeds, and no neutron star, no exotic Xon star, could produce that density. Gindel's and GZ's results matched Einstein's predictions for how light and matter behave in intense gravitational fields. In fact, they confirmed one of the core tests of general relativity, the gravitational redshift, the stretching of light waves as they escape a strong gravitational field. In 2018, when S2 made its closest approach to Sagittarius A*, its light shifted toward the red end of the spectrum by the exact amount general relativity predicted. It was direct evidence that spacetime near the galactic center behaves exactly as Einstein described over a century ago. Andrea GZ later said in an interview with NASA, "What we've observed is the first confirmation of Einstein's theory of general relativity in such an extreme environment." Her words carried quiet weight, not just for physics, but for our understanding of what lies beneath that veil of darkness. To appreciate the scale, think of the orbit itself. When S2 swings closest to Sagittarius A*, the distance between them is only about 120 astronomical units, roughly 3 times the distance between Pluto and the Sunday. For an object weighing millions of suns to fit inside that space, the density must be so high that even light cannot escape its pull. That's what defines the event horizon, not a surface, but a boundary beyond which escape becomes impossible. The orbit of S2 didn't just confirm the black hole's mass, it allowed scientists to map its gravitational field in exquisite detail. They could see subtle shifts in the star's trajectory caused by gravitational time dilation, where time itself slows down near the black hole compared to farther away. In other words, when S2 grazes the black hole's edge, its clock ticks slower than ours. That is not a metaphor. It's measurable physics. For more than 20 years, both teams recorded this celestial dance. It required the world's largest telescopes, the steadiest instrumentation, and the most precise math in astronomy. Each observation refined our understanding of Sagittarius A*, narrowing uncertainties until the data left no alternative explanation. In 2020, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics jointly to Reinhard Gendel and Andrea GZ for the discovery of a supermassive compact object at the center of our galaxy. It was the culmination of 3 decades of work, from nightly observations to complex gravitational modeling. NASA described it as a triumph of persistence and precision. But the confirmation of Sagittarius at times as a black hole is not just a technical victory. It is a milestone in understanding gravity itself. Until then, general relativity had been tested mostly in our solar system and with neutron stars where gravity is strong but not extreme. The galactic center, however, is a natural laboratory where spacetime bends so severely that light curves and orbits precess, meaning they trace tiny spirals instead of perfect ellipses. The measured precession of S2's orbit, about 1/10th of a degree per orbit, matched Einstein's equations precisely. These measurements gave us something we had never had before, a way to test relativity, not in theory, but in motion. Watching a real star trace a path through warped spacetime, every data point confirmed that gravity near Sagittarius at times behaves exactly as relativity predicts. And even as we proved it, we also discovered something else, a kind of cosmic humility. The black hole's presence doesn't announce itself with violence or light, but with precision. Every orbit, every redshift, every delay of light waves whispers the same truth, that spacetime itself is the instrument we are reading. Still, there are puzzles left. Sagittarius at times is one of the quietest black holes known. Why does it feed so little compared to others? Why does its magnetic field produce occasional flares but no steady jet? These are questions that current instruments like Chandra ALMA and the Event Horizon Telescope continue to study. The next generation EHT will capture the polarization of light more clearly, revealing how magnetic fields twist near the event horizon. Meanwhile, new missions are expanding what we can see. The James Webb Space Telescope, JWST, now observes the galactic center in infrared wavelengths that no ground-based telescope can match. It can watch S2 and other stars even closer to Sagittarius A*, track the heating of dust clouds, and detect subtle gravitational effects over time. ESA's upcoming LISA mission, the Laser Interferometer Space Antenna, will detect gravitational waves from supermassive black hole mergers, letting us hear in spacing what our telescopes see in light. Each instrument adds another layer to the same picture. An invisible object confirmed by its gravitational pull, its time distortions, its redshifts, and finally its shadow. As Einstein once said, the important thing is not to stop questioning. We now have the evidence he never saw, the living proof that his equations describe the heart of our own galaxy. So when you picture the Milky Way tonight, know that its calm spiral hides an immense curvature of space, a silent engine that binds everything together, and all of it, from the gentle flicker of S2 to the vast radio glow we now map, fits the same elegant geometry. But as with every great discovery, one question opens another. If we can trace a single star to prove what lies at the center of our galaxy, could we someday measure the heartbeat of other galaxies too and find that the same law of gravity rules them all? Part 3. What lies just beyond the event horizon? At the edge of Sagittarius A*, there is no surface, no rock, no solid boundary, no final layer of matter. Instead, there is a limit, a threshold so absolute that even light, traveling at 299,792 kilometers per second, cannot escape once it crosses it. This invisible frontier is called the event horizon, and just beyond it, the laws of physics, as we know them, stop working. For the first time in human history, in May 2022, we saw its outline, not in visible light, but in radio waves, gathered by a global network of telescopes called the Event Horizon Telescope, EHT. What appeared in that image was a dim glowing ring surrounding a perfectly dark center, a cosmic shadow cast not by a physical object, but by spacetime itself. The ring measured roughly 12 million km across, a scale that matched precisely what Einstein's equations predicted for a black hole of 4.1 million solar masses. That number 12 million kilometers is not random. It comes from a calculation called the Schwarzschild radius, the critical distance from the center of a mass at which escape velocity equals the speed of light. In simple terms, if you tried to leave from inside that radius, even traveling at light speed, you would never get out. For Sagittarius A*, that radius defines the size of its event horizon. The idea of such a boundary was first derived over a century ago by the German physicist Karl Schwarz, who, while serving on the front lines of World War I, solved Einstein's newly published field equations of general relativity. He sent his solution to Einstein in 1916, a precise mathematical description of the gravitational field around a spherical mass. Einstein was astonished. In a letter, he wrote, "I had not expected that one could obtain such an exact solution. Schwarz's radius, though purely theoretical at the time, predicted something extraordinary, that gravity could curve space and time so intensely that all paths, even those of light, would bend inward. That was the first clue that black holes were not just mathematical curiosities, but inevitable outcomes of physics itself." Now, more than 100 years later, Sagittarius A times proves him right. When the EHT combined data from observatories in Chile, Hawaii, Spain, Mexico, Arizona, and the South Pole. The interference patterns revealed that precise curvature. Every photon of light from the gas swirling near the event horizon was bent, twisted, and lensed around the hole, forming the bright circular ring that we see. NASA called it a direct confirmation that Einstein's theory still holds even at the edge of extreme gravity. So what actually happens near that edge? Imagine you're in a spacecraft approaching Sagittarius A*. Long before reaching the event horizon, you'd already noticed something strange. Light begins to curve. Photons that would normally travel in straight lines start to orbit the black hole trapped in circular paths. This region is known as the photon sphere, and for Sagittarius A*, it lies just outside the event horizon at about 1.5 times the Schwarzschild radius. Inside this zone, physics becomes distorted in measurable ways. Time slows down. The closer you get to the event horizon, the slower your clock runs relative to someone far away. This effect is called gravitational time dilation, and it's not theoretical. It's been measured by satellites orbiting Earth and confirmed in every precision test of general relativity near a supermassive black hole. However, it becomes profound. If one observer hovered near the event horizon and another stayed far from it, only minutes might pass for the first, while thousands of years would go by for the second. Einstein described it as a warping of spacing. Matter tells space how to curve and space tells matter how to move. Near Sagittarius A*, that curvature is so extreme that time itself bends with it. From our distant perspective, anything falling in appears to slow down, dim, and eventually freeze at the pearl edge. Never quite crossing, but for the falling object, it continues inward freely, reaching the horizon and vanishing in finite time. This dual perception, where both realities are true, depending on where you stand, is one of the most mind-bending consequences of relativity. NASA scientists describe it as the ultimate trick of light and time. The EHT's 2022 image shows us this effect frozen in light. The glowing ring you see is not material orbiting on a solid surface, but hot gas compressed and heated as it falls inward. The light we detect comes from particles in the accretion flow that reach temperatures of millions of degrees before disappearing into the black hole. Because gravity bends their emission paths, we see a ring brighter on one side, the side where plasma moves toward us, its light boosted by relativistic Doppler effects. Every pixel of that image encodes information about curved spacetime. The ring's thickness, its brightness, and its polarization patterns reveal the magnetic fields threading through the plasma near the horizon. Using these details, scientists reconstructed not just a picture, but a map of spacetime curvature, the way gravity itself shapes light. When compared with simulations, the results were remarkably precise. Einstein's equations, first written in 1915, still describe the behavior of light and gravity perfectly in this extreme regime. As the EHT collaboration wrote, the consistency between observation and prediction strengthens our confidence that general relativity remains an accurate description of nature. And yet, even with this precision, the region just beyond the event horizon remains one of the least understood environments in the universe. This is where magnetic turbulence, plasma dynamics, and possibly quantum gravity effects begin to interact. No human instrument can see inside the event horizon, but everything just outside it leaves visible fingerprints. Consider the flares seen by NASA's Chandra X-ray Observatory. They occur when magnetic fields near the horizon reconnect, snapping and releasing energy equivalent to millions of nuclear explosions. These outbursts are short, lasting minutes to hours, but they tell us how matter behaves when caught between falling inward and escaping outward. By tracking their timing and brightness, astronomers can infer how plasma spirals, how fast the black hole spins, and how strong its magnetic field really is. And spin may be the next big question. Every black hole can rotate, twisting spacetime around it in a phenomenon called frame dragging. If Sagittarius A time spins rapidly, it would drag nearby space like a whirlpool pulls water, slightly altering the orbits of surrounding gas and stars. Future EHT observations and polarimetric data will refine this measurement, giving us the first accurate value of our black hole's rotation rate. When you think about it, the precision of all this is extraordinary. We are measuring motions near an object 26,000 light-years away, where distances are in billions of kilohm. Yet, we can track stars that move the width of a coin held at the distance of the moon. We can measure how light bends around a black hole that weighs 4 million suns, and use that to confirm equations written with pencil and paper more than a century ago. As NASA summarized in its official statement, the EHT has given us the most compelling visual evidence yet that black holes are real and that general relativity remains our best description of gravity. ESA's researchers echoed the same sentiment. The shadow of Sagittarius at times is a milestone, a window into curved space-time. It's important to remember that what we see is ancient light. The radio waves captured in 2017 took 26,000 years to reach Earth. By the time they arrived, human civilization had only just begun to build its first cities. Every image of Sagittarius at times is already history, a frozen moment from a time before recorded human knowledge. And what we've learned from that light is clear. Space and time are not separate entities. They are woven together into a single fabric that stretches, bends, and curves under the influence of mass and energy. Sagittarius at times is the most direct expression of that curvature. So what lies just beyond the event horizon? A world where our current laws of physics still hold. Barely beyond that line, we can't observe. But, right at its edge, we can test every equation we've ever written about gravity. It is where relativity proves itself, where photons trace the boundary between visibility, oblivion, and where the universe reminds us that even invisibility has structure. But one question remains. If everything that crosses the event horizon is lost to observation, what happens to the information it carries? Does it vanish forever? Or does the universe find a way to preserve it? That paradox, the mystery of where information goes when it falls into a black hole, is where our next journey leads in part 4. Why is our black hole so quiet? Most black holes feed with fury across the distant universe. They blaze like beacons, quasars so bright that they outshine entire galaxies. Their disks of infalling gas radiate with the power of trillions of suns, and their jets tear across intergalactic space. But at the center of our own galaxy, the story is different. Sagittarius A*, the Milky Way's supermassive black hole, barely glows at all. It sits quietly, releasing only faint bursts of X-rays and infrared light every now and then, as if exhaling after eons of silence. For an object that could easily swallow worlds, it seems unusually calm, underfed, almost dormant. Astronomers call it a low luminosity active galactic nucleus, or LLGM, a black hole that's active, but only faintly so. To understand why, we must first know how black holes eat. When gas, dust, or a wandering star drifts too close, the black hole's gravity pulls it inward. But that matter doesn't fall straight in. It spirals, forming a thin rotating disk, called an accretion disk. Friction and magnetic turbulence within that disk heat the gas to millions of degrees, causing it to emit radiation across the spectrum from visible light to X-rays. In most galaxies, this process is violent, efficient, and luminous. In Sagittarius A*, it's not. Measurements from NASA's Chandra X-ray Observatory, ISA's XMM Newton, and the Atacama Large Millimeter Submil Array show that Sagittarius A times consumes only a tiny fraction of the material available to it, perhaps as little as 1/millionth of its Eddington limit, the theoretical maximum rate at which it could accrete before radiation pressure pushes material away. In other words, our galactic black hole eats less in a year than an average quasar consumes in a single minute. So why does it starve in a galaxy full of gas? Part of the answer lies in its surroundings. Sagittarius A times sits in a relatively calm region of space. The dense, molecular clouds that might feed it are hundreds of light-years away, and the stellar winds from nearby stars tend to push gas away rather than funnel it in. Even when material does fall toward it, most of it never reaches the event horizon. Instead, it circles in chaotic flows, called radiatively inefficient accretion flows or reoffs. hot diffused plasma in which only a small portion of matter actually crosses the horizon. In these flows, the gas is so thin that it cannot cool efficiently by radiation. Instead of collapsing into a bright thin disk, it expands into a hot puffy cloud that emits only weakly in X-rays. NASA researchers describe it as a black hole running on an empty tank. Yet even in its quiet state, Sagittarius A is not completely still. Every few hours, Chandra and Keck Observatory detects short flares of light, spikes that can be 100 times brighter than its usual emission but last only about an hour. These flares are believed to arise from magnetic reconnection, events where tangled magnetic field lines snap and reconnect near the event horizon, releasing bursts of energy that accelerate electrons almost to the speed of light. The same mechanism powers solar flares on the sun, but here it happens in a gravitational field millions of times stronger. The pattern of these flares tells us something about the magnetic field geometry near the black hole. Polarization measurements from the Event Horizon Telescope (EHT) show that light emitted near Sagittarius A is strongly polarized, meaning it carries the imprint of magnetic fields twisting around the black hole. By comparing this polarization with models, scientists found that the fields are highly ordered, not random, a signature of a magnetically dominated accretion flow. As the EHT team summarized, the magnetic field structure near Sagittarius A suggests that the black hole's dynamics are governed by magnetized plasma rather than purely by gravity. This discovery connects our black hole to a broader class of cosmic objects, magnetically arrested disks, MADS, in which magnetic pressure resists the infall of gas, throttling the accretion rate. In effect, Sagittarius A might be choked by its own magnetic field, a cosmic feedback loop that limits how much matter can enter at once. This could explain why it shines so faintly. It's not that there's no fuel, but that the fuel can't reach the engine. Another piece of the puzzle comes from the Fermi bubbles, vast lows of gamma radiation extending 25,000 light-years above and below the galactic plane. They are evidence that Sagittarius A was not always quiet. Roughly 6 million years ago, it likely went through a bright active phase, swallowing large amounts of gas and emitting jets powerful enough to carve those bubbles into the surrounding halo. Now it rests, a black hole between cycles. Such feeding cycles are common in the universe. Black holes appear to alternate between active and quiescent states depending on how much material flows into them. When gas supply increases, the accretion disk becomes denser. Radiation pressure rises and the system ignites as a quasar. When the supply dwindles, radiation fades, and the disk thins until only occasional flares remain. Sagittarius A happens to be in one of those quieter epochs. To see this, consider the balance between gravity and radiation. At high accretion rates, the pressure of radiation pushes outward, resisting gravity and shaping the disk. At extremely low accretion rates, that pressure becomes negligible and the gas instead becomes dominated by magnetic and kinetic energy. Turbulent, unstable, but dim. This transition between efficient and inefficient accretion is one of the keys to understanding how galaxies evolve. For example, galaxies with bright quasars often show star formation suppression. Radiation from their active nuclei heats the surrounding gas, preventing new stars from forming. But in galaxies like ours with a quiet black hole, that radiation feedback is minimal, allowing gas clouds to cool and collapse into stars. So, Sagittarius A** phase might actually help sustain star formation in the Milky Way's central region. There's also a fascinating link between the quietness of Sagittarius A and its spin. If the black hole rotates slowly, its ability to generate strong jets and magnetic amplification diminishes. This would naturally make it dimmer and less active. Future data from the next generation EHT, combined with JWST's infrared monitoring, may soon measure its spin more precisely. By observing how gas close to the event horizon drifts, twists, and polarizes light. But there's another possibility. Some simulations suggest that even with low feeding rates, the accretion process might occasionally clog. storing magnetic energy until it suddenly releases in a flare. This could explain why we see Sagittarius at times burst in brief, unpredictable flashes. It's not asleep, only pausing between breaths. In 2019, NASA's Chandra X-ray Observatory captured the brightest flare ever seen from Sagittarius A. It brightened by a factor of 75 over its usual level in just a few minutes, then faded again. Astronomers still don't fully understand what triggered it, but one hypothesis involves a fragment of a disrupted asteroid or comet falling too close to the horizon, releasing a pulse of energy before disappearing. As one researcher at the Center for Astrophysics put it, it's as if the black hole burped. These fleeting events remind us that Sagittarius at times is not inert. It's dynamic, responsive, and deeply complex. Even in stillness, it sculpts its surroundings. Magnetic turbulence, plasma loops, and occasional infalling debris combine to form a system delicately balanced between gravity and chaos. Meanwhile, new tools are preparing to study this quiet titan more closely. The James Webb Space Telescope, JWST, observes the galactic center in mid-infrared light, capturing structures within the surrounding dust clouds that feed the black hole. The Imaging X-ray Polarimetry Explorer, 9SP launched by NASA measures how X-ray light is polarized as it escapes from the accretion flow, a direct way to map the geometry of magnetic fields near the horizon. Together, these missions are transforming our view of low luminosity black holes from static to dynamic, revealing how even the quietest ones remain alive with hidden energy. Scientists describe Sagittarius at times as a black hole in a state of balance, not growing, not fading, but breathing slowly with the galaxy itself. And perhaps that's the most precise description we can give, because in the great life cycle of galaxies, black holes like this do not remain silent forever. Their quiet phases are pauses, intervals between bursts of activity that can reshape an entire galaxy's destiny. When Sagittarius A times wakes again, it may once more send jets of energy across tens of thousands of light years, altering the Milky Way's future. For now, though, it rests calm, faint and steady, a gravitational giant between meals. Its silence is not absence but potential, waiting, and that stillness leads to one more question. If Sagittarius at times is sleeping, what exactly triggers its awakening? Part 5. Could it be something else entirely? What if the dark center of the Milky Way is not a black hole at all? What if the same gravity, the same orbits, the same faint flares could be explained by a different kind of object, one with no event horizon, no true shadow, no point of no return? That question has guided a quiet, rigorous effort in astrophysics for decades. To answer it, scientists have tested serious alternatives to a supermassive black hole at Sagittarius A*, boson stars, quasars, and extremely dense clusters of dark or ordinary remnants. Each idea comes with predictions we can compare against observations, radio spectra, polarization patterns, precise stellar orbits, and horizon-scale images. Let's take them one by one, gently and carefully, the way a lab notebook turns its pages. First, the dense cluster hypothesis. Imagine packing neutron stars, stellar mass black holes, or brown dwarfs into the central 100 astronomical units, a volume smaller than the orbit of Neptune, until their combined gravity mimics a single heavier object. On paper, such a cluster can reach a mass near 4.1 million suns, but clusters have lifetimes. In a region that dense, objects collide, merge, and scatter. Two body encounters slowly evaporate. The cluster and the system collapses or disperses on timescales much shorter than the age of the Milky Way's bulge. Calculations show that a cluster compact enough to drive S2 to 7600 kilometers per second would become unstable in far less than a million years. A brief moment compared to billions of years of galactic history. We would be extraordinarily lucky to catch such a transient arrangement exactly now. Worse for the cluster idea. A swarm of compact objects at those densities should light the center with X-ray binaries, collisions, and tidal disruptions far more often than we observe. Instead, the galactic core is faint with low steady luminosity and rare flares. Infrared astrometry provides a second, sharper test. The orbits of stars like S2 constrain not just the total mass but how concentrated it is. Over decades, teams led by Reinhard Genzel and Andrea Gzi mapped these orbits with millisecond precision and found that almost all the mass is confined within a region no larger than our solar system. If part of the mass were spread out, as in a cluster, the orbits would show extra precession, subtle tugs, and deviations we do not see. The data point to a single, extremely compact source. Next, boson stars. These are hypothetical objects made of ultralight particles, XANs, that can overlap in the same quantum state, forming a smooth self-gravitating lump of field rather than a star built from atoms. Without a hard surface and without an event horizon, a boson star could in principle imitate some black hole-like gravity while avoiding a point singularity. Could such an object sit at the center of the Milky Way? There are clear signatures to check. A boson star's density profile is extended, not as sharply concentrated as a black hole. Close orbits would feel that extension. S2 would not sweep through pericenter with the same relativistic precession we've measured. The gravitational redshift of its light at closest approach would differ from the precise value observed in 2018, but the observed redshift matched general relativity's black hole prediction and the precession angle fits a compact horizon scale source. Further horizon scale imaging matters. The Event Horizon Telescope, a ring size around Sagittarius A*, about 12 million kilometers across, is set by spactime lensing very close to the photon orbit of a black hole. Extended objects without horizons tend to produce different ring structures, sometimes smaller, sometimes with central brightness from a surface. The EHT team reported that Sagittarius A*'s appearance is remarkably consistent with the predictions of general relativity. The diameter and symmetry match simulations of a low-luminosity black hole with a weak hot accretion flow. Polarization adds another check. The EHT polarization maps show ordered magnetic fields threading the plasma right outside the dark center, a pattern reproduced by GRMHD, general relativistic magnetohydrodynamics, models of accretion onto a black hole. Boson star models can host magnetic fields, but reproducing the same ring scale and polarization structure without a horizon generally requires tuning the particle mass and configuration in ways that struggle against other constraints. Then gravitational vacuum stars. They replace the interior with an exotic vacuum state and a thin shell, avoiding the singularity while mimicking much of a black hole's external field. Unlike black holes though, grav stars possess a surface just outside where the horizon would be. Matter falling and must hit that surface. If so, the energy would be released as radiation, a soft afterglow from accumulated material instead of disappearing. For Sagittarius A*, decades of observations set tight upper limits on any surface emission in the sub-millimeter and infrared bands. We do not see the persistent thermal light that a surface would naturally produce from the continuous drizzle of inflowing gas. As one EHT analysis phrased it, this absence strongly disfavors horizonless surfaces at the galactic center. Radio properties strengthen the case. Sagittarius A time shows a sub-millimeter bump in its spectrum near 230 GHz where the flow becomes optically thin and we glimpse emission from the innermost orbits. Very long baseline measurements find a size-frequency relation that shrinks toward this band consistent with a compact photosphere near a horizon. A true surface or extended core often imprints different spectral slopes and sizes at these frequencies. The variability is a further clue. Sagittarius at times flickers on minute scale times, the dynamical time scale expected for plasma orbiting just a few Schwarzschild-Radii from a 4 million solar mass black hole. Boson star and Gravis star configurations can vary, but matching both the timescale and the statistics of the flares as seen by Chandra XMM Newton KEK and VLT naturally falls out of hot magnetized plasma skimming a horizon. What about dark matter cores or spikes? Some models predict a steep pileup of dark matter toward the center, but the distribution would be gradual, not point-like, and would not produce the clean horizon scale ring seen by the EHT. Moreover, dark matter interacts weakly, so it struggles to sustain the hot polarized emission and minute scale dynamics observed at millimeter wavelengths. A valuable surface test comes from simple bookkeeping. If gas falls onto a surface, energy must radiate somewhere. For Sagittarius A*, even its low accretion rate would build up heat on any surface slightly larger than our horizon, producing persistent infrared light that our instruments would detect. We do not detect it. NASA summarized this logic succinctly in black hole studies. Matter hitting a surface must glow. Matter crossing an event horizon does not. History has also supplied natural experiments. In 2014, the dusty object G2 passed near Sagittarius A*. Some predicted a dramatic brightening if a solid surface or dense medium surrounded the center. Instead, the emission rose modestly and returned to baseline, behavior consistent with a sparse hot accretion flow and no surface waiting to catch the debris. To keep our comparisons grounded, here is a COM checklist. How each alternative fares against key observations. Stellar orbits S2 demand 4.1 million solar masses inside a region smaller than the solar system. Dense cluster unstable online short time. Scales would overproduce X-ray activity. Boson star extended potential struggles. With the exact gravitational redshift and precession measured. GRAR can mimic mass but introduces a surface that should glow. Black hole matches mass, concentration and relativistic effects. 8-ring 2022 to 12 million kilometers diameter. Correct asymmetry in thickness. Polarization. Consistent with ordered fields near our horizon. Dense cluster. No ring at a single compact radius. Boson star. Possible rings but typically different. Size and central brightness. Tuning required. Gravis star. A surface would add extra emission or echoes. Not observed. Black hole reproduces ring, size, polarization, and variability with GRMHD models. Spectrum and variability. Sub-millimeter bump. Minute scale. Flicker. Dense cluster. Dark matter core. Extended emission. Wrong time. Scales. Horizon objects often predict lingering surface light. Black hole. Hot. Inner flow explains both the spectrum and the fast fluctuations. Where does this leave us? Every major line of evidence, orbits, ring size, polarization, spectrum, and variability, points to the same conclusion. A supermassive black hole. ESA's language for the EHT result is plain. The shadow of Sagittarius A times is a milestone, a window into curved spaceme. NASA describes the broader picture as the most compelling visual evidence yet, that black holes are real. And yet, science is careful with the word proof. Alternatives are not discarded by opinion, they are narrowed by measurement. Some Boson star models can still be arranged to resemble a black hole, closely at current precision. GRAR constructions continue to be explored in theory, testing whether a surface could be hidden beneath plasma effects. New kinds of ultrate dark matter are being modeled near galactic centers. That is why the next measurements matter. A pulsar, a fast-spinning neutron star in a tight orbit around Sagittarius 8 times would act like a perfect clock, letting us map spacing with exquisite detail and distinguish horizons from surfaces. Searches continue with radio arrays. A discovery there would be transformative. Improved polarimetry with the next generation EHT will refine the magnetic field geometry and the black hole spin, reducing the wiggle room for horizontal models. And long baseline monitoring with JWST, KEK and VT will track even closer stars, tightening the mass and concentration constraints. Further still, behind each step sits a story of craft. The patient nightly imaging that drew star ellipses one dot at a time. The data flights carrying petabytes of EHT recordings on hard drives from the South Pole to correlation centers. The polarization maps that turned chaotic flicker into ordered field lines taken together. They do not just point somewhere, they converge. So yes, we have tested other possibilities and we continue to test them. But each new observation pushes the alternatives into tighter corners while the black hole model remains consistent across Independent methods. As one EHT scientist put it, if it walks like a black hole, talks like a black hole, and casts a shadow like a black hole, the sentence finishes itself. There is one more piece to place in it, is visual. How do you turn a planet's worth of radio dishes into a single lens sharp enough to outline a shadow? How do you freeze a target that changes in minutes and still recover the true ring? Part 6. How did we finally see its shadow? For a century, black holes were the ultimate invisible objects. We could feel their pull, measure their mass, trace the paths of stars orbiting, their gravity, but never actually see one. Even light, the fastest thing in the universe, could not escape their grasp. So, how could we ever hope to capture an image of something that does not emit light? That question, once thought impossible, was answered by an instrument the size of our planet. In 2017, 8 observatories scattered across the globe joined together to form the Event Horizon Telescope, or EHT, a synchronized network designed to act as one enormous Earth-sized radio dish. Its purpose was simple in theory but daunting in practice: to directly observe the shadow cast by a black hole's event horizon. To understand how this was done, imagine trying to photograph a donut on the surface of the moon. That is roughly equivalent to what astronomers attempted when targeting Sagittarius A*, the supermassive black hole at the heart of our galaxy, 26,000 light-years away. The resolution required was about 20 microarc-seconds, so fine that a single optical telescope, no matter how large, could never achieve it. But by using a technique called Very Long Baseline Interferometry, or VBI, the EHT team could combine the signals from multiple radio telescopes spread across Earth, effectively turning our planet into a single rotating lens. Here's how it worked. Each observatory, from ALMA in Chile's Atacama Desert to the Submillimeter Array in Hawaii to the South Pole Telescope, recorded radio waves at a wavelength of 1.3 millimeters where the gas surrounding black hole shines brightest. Every site was equipped with hydrogen Maya atomic clocks accurate to within a billionth of a second, ensuring that all observations were synchronized to the same cosmic moment. The data from each telescope was stored on hard drives, not sent through the internet but flown by airplane to supercomputing centers at the MIT Haystack Observatory in the United States and the Max Planck Institute for Radio Astronomy in Germany. In total, they gathered about 4 petabytes of raw data, roughly the same as all photos uploaded to social media over several days worldwide. Processing that mountain of information required specialized algorithms to reconstruct an image from the interference patterns recorded between telescopes. Each pair of observatories acted as one enormous virtual baseline, measuring how incoming waves from the target interfered with each other. The longer the distance between telescopes, the finer the detail they could resolve. As Earth rotated, those baselines changed direction, filling in the missing gaps in the image like a cosmic scanner slowly drawing a picture line by line. But Sagittarius A times posed unique challenges. Unlike M87*, the black hole in the giant elliptical galaxy, Messier 87, first imaged by the EHT in 2019, our Milky Way's central black hole is 1,500 times smaller in diameter. Its plasma orbits hundreds of times faster, meaning that its appearance changes from minute to minute. To make matters worse, we observe it through the thick disk of the Milky Way, where interstellar gas and dust scatter radio waves, blurring the image like heat rippling over a desert road. Capturing a stable picture under those conditions was like photographing a candle flame flickering behind a waterfall. To overcome this, the EHT team developed advanced imaging algorithms that could handle incomplete time-varying data. Multiple independent pipelines, using different reconstruction methods, were run in parallel to prevent bias. The results were then compared, tested, and averaged, producing a final consensus image that was statistically robust. When the image was released in May 2022, it showed a bright ring of emissions surrounding a dark core exactly where Einstein's theory predicted the shadow should be. The measured ring diameter, about 12 million km, was consistent with a black hole of 4.1 million solar masses. The brightness on one side, the asymmetry in the ring, came from gas moving toward us at near light speeds, its radiation boosted by relativistic Doppler effects. The faint side was light moving away, its energy redshifted by gravity. Together, these features revealed not only the black hole's size, but also its spin orientation and the geometry of the accretion flow. NASA described the result as a direct view of the boundary between the known and the unknowable, and ESA echoed the sentiment. The shadow of Sagittarius at times confirms yet again the predictions of general relativity in the strongest gravitational field we can access. But how does one turn faint scattered radio waves into a single sharp image? The process begins with correlation. At MIT and Max Planck, teams aligned the signals from each telescope down to the nancond, correcting for Earth's rotation, atmospheric delay, and clock drift. From those aligned signals, they calculated visibility, amplitudes, and phases, quantities that describe how the brightness of the source changes across the sky. Mathematically, it's like assembling a jigsaw puzzle where each piece represents a frequency component of the original image. When combined through an inverse Fourier transform, the pieces reveal a complete picture. Yet, the EHT doesn't collect all possible baselines. There are gaps in coverage. To fill them, scientists use regularized maximum likelihood methods, statistical tools that find the simplest image consistent with the data and with known physics such as the expected ring structure from general relativity. Each reconstruction was tested against simulated data generated by general relativistic magnetohydrodynamic GRMHD models, detailed computer simulations of how magnetized plasma behaves near an event horizon. The final match between simulation and observation was striking, but there's another subtlety that makes Sagittarius at times especially tricky: time variability. Because its material orbits every few minutes, any single observation captures a slightly different snapshot. Instead of one frozen picture, the EHT image represents an average of many fleeting moments, like a long exposure photograph of moving lights. To account for this, researchers generated thousands of model frames, then compared them statistically to the data to find which configuration best fit the observed visibilities. The result wasn't just a picture. It was a dynamic model of our galaxy's core. It told us the ring's size, shape, orientation, and brightness distribution. It revealed magnetic field structures, and it constrained how fast the black hole must spin. All of this emerged from radio waves, invisible to the human eye, converted to digital signals, synchronized across continents, and rebuilt by algorithms, guided by Einstein's mathematics. One of the most extraordinary parts of the EHT story lies not in the telescopes themselves, but in the people. Hundreds of scientists, engineers, and software specialists from around the world, more than 300 researchers across 80 institutions, worked together for over a decade. In 2019, their collaboration produced humanity's first direct image of a black hole M87* in the galaxy Messier 87, 55 million light-years away. That black hole is enormous, 6.5 billion times the Sun's mass, and changes slowly, allowing the EHT to reconstruct a static image more easily. But Sagittarius A*, being smaller and faster, was a tougher challenge, one that required both improved techniques and immense patience to help stabilize the reconstruction. The EHT used ALMA, the most sensitive array in the world, as its anchor. Almost 66 antennas acted together as one gigantic receiver, dramatically increasing the overall sensitivity of the network. At the opposite end of the Earth, the South Pole Telescope provided the longest possible baseline, improving resolution to the microarch-second level. Every telescope's participation was crucial, removing even one left holes in the data, like missing pixels in a photograph. To test for reliability, the team divided into 4 independent imaging groups, each using different mathematical methods: clean, MEM, regularized maximum, likelihood, RML, and diff-map. They worked without sharing results, then compared outcomes months later. All 4 groups produced the same fundamental structure, a ring about 50 microarcsec across with a dark center. It was the shadow, the first ever seen of our own galaxy's black hole. And, despite being faint and variable, it agreed perfectly with general relativity. ESA summarized the achievement as a global effort that turned Earth into a telescope. NASA called it an unprecedented technical triumph. Beyond the science, the image carries a quiet significance. For the first time, we are looking directly at the place where space and time collapse into one. Every photon in that image has been bent by gravity into a near-perfect circle, tracing the geometry of spacetime itself. As one EHT scientist said, "We are seeing what we once thought could never be seen." The next goal is motion, not a still photograph, but a movie. The EHT continues to collect data each year, and with improvements in sensitivity and additional telescopes joining the array, including NOMA in France and the Greenland telescope, the network's resolving power grows. Future observations will allow researchers to watch the plasma near Sagittarius A times evolve in real time, perhaps even tracking orbiting hotspots circling the event horizon. It will be the first time humanity watches spacetime itself in motion. In the words of Shepard Dwellerman, the EHT's founding director, this is the dawn of a new era in black hole astronomy. From invisible gravity to visible proof, the journey from Einstein's equations in 1915 to a glowing ring in 2022 is one of the most profound accomplishments in modern science. The telescope that sees the unseeable has opened a door, and beyond that door lies the most extreme environment we can study. But one mystery remains unsolved. If we can now see the shadow of a black hole, can we also see the forces that give rise to its unpredictable flares and storms? Part 7. What happens when magnetic fields collide near the core? At the edge of Sagittarius A*, gravity is not the only force at work. Something equally powerful and far more unpredictable is moving through the plasma that surrounds it. Invisible lines of magnetic energy twist, snap, and reconnect, releasing bursts of radiation that light up the galactic center. When these invisible fields collide, space itself flickers. This is where the story of magnetic reconnection begins, one of the most dynamic and least understood processes in all of astrophysics. It is the same process that powers solar flares on the sun, drives auroras in Earth's upper atmosphere, and releases the sudden flashes of X-rays and infrared light that astronomers detect near our galaxy's supermassive black hole. In the extreme environment just outside Sagittarius A*'s event horizon, plasma and magnetic fields dance to the rhythm of relativity. To picture this, imagine gas spiraling toward the black hole, drawn inward by gravity, but resisting through motion. That gas is ionized, its atoms stripped of electrons by heat, reaching tens of billions of degrees Kelvin. The result is plasma, a sea of charged particles that move collectively under the influence of magnetic and electric fields. In plasma, magnetic field lines behave almost like elastic threads frozen into the flow. They move and twist with the particles themselves. As the gas swirls around Sagittarius A*, these lines are stretched and tangled by rotation and turbulence. At certain points, opposite field lines collide and reconnect, releasing vast amounts of stored magnetic energy. That sudden conversion magnetic energy into kinetic and thermal energy accelerates electrons to near light speeds, producing the brief flashes of radiation that telescopes detect as flares. The Chandra X-ray Observatory and ESO's Very Large Telescope have observed such flares erupting from Sagittarius 8 times, roughly once a day. Each flare brightens the core by factors of 10 to 100, then fades within about an hour. The time scale fits perfectly with a region just a few Schwarzschild-Radii from the event horizon, where plasma orbits at relativistic velocities. These are not explosions in the ordinary sense, but rather controlled releases, energy drawn from twisted magnetic loops, reconnecting under gravitational shear. When the Event Horizon Telescope turned its polarization-sensitive eyes towards Sagittarius A*, it confirmed. This picture, polarization, is a property of light that tells us about the orientation of the magnetic fields in the region where the light was emitted. By mapping how the direction of polarization changed around the ring, scientists could visualize the structure of those fields, a magnetic fingerprint surrounding the black hole. What they found was extraordinary. The fields were coherent and ordered, wrapping around the shadow like the ribs of a vortex, exactly as predicted by magnetohydrodynamic MHD models. In these models, plasma motion and magnetic forces are inseparable, described by a single framework known as General Relativistic Magnetohydrodynamics, GRMHD. It is an extension of fluid dynamics that includes the effects of strong gravity, relativity, and electromagnetic forces all at once. Numerical simulations using GRMHD show plasma orbiting Sagittarius A times, forming hotspots sheared by rotation and releasing energy through reconnection events. When compared to EHT data, the synthetic polarization maps match the observed structure almost perfectly. Dr. Monika Moshi-Brodska, a key member of the EHT team, summarized it simply: "We are now seeing magnetic fields strong enough to control how matter behaves. Very close to the event horizon, the strength of those fields is immense, roughly 30 to 100 G, thousands of times stronger than Earth's magnetic field, though concentrated within a region only a few million km wide. Such fields dominate the motion of charged particles, channeling them into curved trajectories and sometimes ejecting them outward in narrow jets. Sagittarius A times does not currently produce large jets like the ones seen from M87*, but small-scale outflows have been observed, possibly the remnants of similar processes acting in miniature. And beneath all this, a deeper relativistic effect is at play: frame dragging. According to Einstein's general theory of relativity, a rotating mass drags spacetime itself around with it like a spoon stirring honey near a spinning black hole. This effect is so strong that any nearby matter or magnetic field must rotate in the same direction. This twisting motion winds the field lines even tighter, feeding the cycle of reconnection and flare production. ESA researchers describe the process beautifully in their technical notes. Frame dragging couples the black hole's spin to its magnetic environment, converting rotational energy into radiation. That coupling may also explain why the flares are polarized. As the plasma accelerates along twisted field lines, its emission becomes preferentially aligned, leaving a measurable pattern in the light. By analyzing the polarization angle during a flare, scientists can infer how magnetic loops evolve over minutes, giving the first dynamic glimpse of plasma behavior near a horizon. In 2018, the gravity instrument on the Very Large Telescope Interferometer detected near-infrared hotspots orbiting Sagittarius at times during one such flare. They traced circles roughly 10 million kilometers in radius, completing each orbit in about 45 minutes, speeds approaching 30% of light. The polarization of the light rotated smoothly with the orbit, confirming that the hotspot was magnetically confined, not random turbulence. This was direct evidence that the flares arise from compact plasma regions tied to magnetic loops near the event horizon. The picture that emerges is both consistent and elegant. A rotating black hole drags spacetime. That motion twists magnetic fields. Those fields trap hot plasma, and when the fields reconnect, energy bursts outward as light. Our fleeting window into the invisible. Even the smallest flare from Sagittarius at times carries enormous energy, roughly the output of 1 million suns over several minutes. But compared to the total gravitational energy available, it is only a tiny release. That suggests a vast reservoir of magnetic energy still stored near the horizon, waiting for the next reconnection event. NASA's theoretical models suggest that if the black hole's spin and magnetic field align just right, magnetically arrested disks or mad states can form where magnetic pressure becomes so intense that it temporarily halts in falling matter. When the balance breaks, the trapped plasma collapses inward, releasing a burst, precisely the kind of variability seen in Sagittarius A*. Such episodes could explain why its brightness changes irregularly with calm days punctuated by brief storms of radiation. Although our black hole is relatively quiet now, evidence suggests that it may have been far more active in the past. The discovery of the Fermi bubbles, gigantic lobes of gamma-ray emission, extending 25,000 light-years above and below the galactic plane, points to a period of intense activity several million years ago. Those bubbles could have been inflated by powerful magnetic outflows or jets driven by earlier reconnection events on a galactic scale. Even in its dormant state, Sagittarius A, time still hums with magnetic potential. Looking forward, the next generation EHT, and instruments like IXPE, NASA's Imaging X-ray Polarimetry Explorer are bringing even finer detail to this magnetic story, can measure the direction and degree of polarization in X-rays, giving us direct clues about how magnetic fields evolve during flares. JWST, meanwhile, observes the infrared echoes that follow those bursts, tracing how energy ripples outward through the surrounding gas. These missions are revealing not just a black hole but a living system, one shaped as much by magnetism as by gravity. Each flare, each pulse of polarized light is a message written in plasma telling us how energy moves in the most extreme laboratory nature provides. As one EHT researcher put it, magnetic fields are the heartbeat of a black hole. And the heartbeat continues. With every flare, we learn more about how gravity and magnetism cooperate, two forces that rarely meet so closely anywhere else. It is here at the threshold between energy and emptiness that physics itself reveals its sharpest details. But what happens to the galaxy beyond this small violent heart? How has this central engine, quiet yet powerful, shaped the vast spiral arms that surround it? Part 8. How did Sagittarius A time shape the Milky Way? Every galaxy has a heart, and in that heart lies something so heavy that its gravity sculpts everything around it. Stars, gas, dust, and time itself. For our Milky Way, that sculptor is Sagittarius A*, the supermassive black hole at the center. But here's the question few ever ask. Did the galaxy create the black hole, or did the black hole create the galaxy? Astronomers now suspect the answer is both, over billions of years. Sagittarius A times and the Milky Way have co-evolved, influencing each other in a constant exchange of gravity, gas, and radiation. That partnership has shaped not just the stars we see, but the very structure of the galaxy we call home. Let's start at the beginning. Nearly 13 billion years ago, when the Milky Way was still a chaotic cloud of hydrogen, helium, and dark matter. In those early times, small, protogalactic fragments merged repeatedly, their collisions igniting waves of star formation. Amid the turbulence, massive stars collapsed into black holes. Some of these grew rapidly, swallowing nearby gas and merging with others until one of them, deep in the gravitational center, began to dominate. That object would eventually become Sagittarius A*. Simulations by NASA and ESA's cosmological programs like Illustrious TNG and Eagle show that supermassive black holes and their host galaxies form in lockstep. As galaxies grow through mergers, their central black holes grow through accretion, a steady siphoning of material that releases tremendous energy back into the surrounding medium. This process is called feedback, and it is crucial to galactic evolution. When Sagittarius A times was younger, it likely went through active phases much like the bright quasars we see in distant galaxies today. During those times, it would have devoured vast amounts of gas, heating it to millions of degrees and producing jets of radiation and particles. Those outflows would have pushed against the galaxy's gas clouds, suppressing star formation in some regions while triggering it in others. In effect, the black hole acted like a thermostat for the Milky Way, preventing it from forming too many stars too quickly, ensuring stability over cosmic time. Evidence for this ancient activity still lingers. The Fermi bubbles, massive lows of gamma radiation, discovered by NASA's Fermi Gamma Ray Space Telescope, stretched 25,000 light-years above and below the galactic plane. They are thought to be the fossil remains of an outburst from Sagittarius A times about 6 million years ago. The energy released in that event would have been enough to heat and expel gas far into the galactic halo, reshaping the Milky Way's chemical distribution. That brings us to one of the most striking discoveries in modern astrophysics, the M-sigma relation. This is a mathematical link between the mass of a galaxy's central black hole and the average velocity of stars in its bulge. Galaxies with heavier black holes have faster-moving stars, suggesting that both properties evolved together. In the case of the Milky Way, Sagittarius A times fits the relation almost perfectly, confirming that our galaxy's bulge and its black hole share a connected history. When we look at the Milky Way's central bulge, a densely packed peanut-shaped swarm of ancient stars, we're seeing that history frozen in motion. Infrared surveys from NASA's Spitzer Space Telescope and ESA's GIA mission have mapped its three-dimensional shape in exquisite detail. They reveal a bar-like structure cutting across the center about 27,000 light-years long, made of stars orbiting in elongated loops. The gravity of Sagittarius A acts as the anchor of that bar, keeping the system stable while directing streams of gas inward along its edges. Those gas streams feed both the central black hole and the surrounding star-forming regions, maintaining a cosmic feedback loop that links small and large scales. In the galactic center near the central molecular zone, enormous clouds of gas swirl within a few hundred light-years of Sagittarius A*. Here the interplay between gravity, magnetic fields, and radiation shapes a dense ecosystem of molecular filaments and nent stars. Telescopes like ALMA, the Atacama Large M Submillion Array, and JWST are now mapping these regions, showing how bursts of star formation flare and fade over tens of millions of years. Interestingly, despite its proximity to a supermassive black hole, this region remains one of the most fertile star-forming environments in the galaxy, proof that gravity and creation can coexist in delicate balance. Chemical evidence supports this narrative. Stars near the center contain higher proportions of heavier elements like iron and nickel, the products of earlier generations of supernova. As ESA's Gaia-ESO survey revealed, this metallicity gradient decreases outward from the core. It tells a story of recycling. Older stars enriched the gas, black hole feedback redistributed it, and new stars condensed from that processed material. The galactic bar plays a central role in that recycling process. It acts as a gravitational conveyor belt, channeling gas inward and outward across thousands of light years. When gas moves along the bar toward the center, it compresses and forms stars. When energy from Sagittarius A or supernovae pushes outward, it refreshes the galactic disk with new material. In essence, the bar is both the artery and the heartbeat of the Milky Way. Computer simulations from NASA's AS Research Center and the Max Planck Institute for Astrophysics show this in action. In these models, gas clouds spiral inward along the bar, collide, and fragment. Star clusters ignite near the center, releasing energy that prevents further collapse. A self-regulating mechanism driven by the black hole's gravity and the bar's rotation. When Sagittarius A enters a quiescent phase, star formation rises. When it becomes active again, outflows suppress it. It's a cosmic feedback loop fine-tuned by forces acting across tens of thousands of light years. Astronomers have even traced echoes of past black hole activity reflected off nearby clouds. Using the Chandra X-ray Observatory, scientists detected faint X-ray echoes, light that had bounced off interstellar gas long after the original flare faded. By timing those reflections, they estimated when Sagittarius A last erupted, confirming that it was far more energetic a few hundred years ago than it is today. Each echo is a delayed whisper of a once bright phase. And yet, despite its dormant state, Sagittarius A still exerts subtle control over the Milky Way's dynamics. Through gravity alone, it stabilizes the orbits of stars in the bulge and governs how gas flows through the bar. Without such a central mass, simulations show that the bar would slowly dissolve and the spiral structure could lose coherence. Our galaxy's symmetry, its ordered spin and layered beauty depends in part on that dark anchor at its core. NASA astrophysicist Dr. Julie Comerford once said, "Submassive black holes and their galaxies are locked in a cosmic dance, each one shaping the other's steps, and Sagittarius A is our partner in that dance. Steady, quiet, but decisive. Even now at 26,000 light-years from Earth, the subtle gravitational influence of Sagittarius A extends far beyond the central bulge. It affects how stars move in the inner disk and how spiral arms maintain their rhythm. As gas drifts inward along the spiral arms, it joins the circulation of the bar where it can be recycled or consumed. This large-scale motion is what keeps the Milky Way alive. A system balanced between inflow and feedback, attraction and release. The ongoing Gaia mission continues to refine this understanding. By tracking the positions and motions of over 1.8 billion stars, Gaia has mapped subtle patterns of rotation and migration that trace back to the central gravitational well. Its data suggests that even stars far from the core feel the heartbeat of Sagittarius at times through the overall galactic potential. In short, every star in the Milky Way, including our Sun, moves to a rhythm set in part by the mass at the center. Herschel Space Observatory and Planck missions added another layer of detail. By mapping the dust and gas distribution across the galactic plane, they revealed streams of material connecting the inner bulge to the outer arms, indicating that the Milky Way is not static, but constantly exchanging matter across its entire disk. This dynamic circulation ensures that the galaxy continues to evolve, quietly, slowly over billions of years. When viewed through this lens, Sagittarius A is not just a black hole. It is an engine of order in a system of chaos. Its gravity gives the Milky Way a center, a frame of reference around which everything else can rotate. Its past eruptions seeded the halo with energy and metals. Its current calmness allows stars like our Sun to form and orbit in peace. And perhaps most remarkable of all, the Milky Way is just one of hundreds of billions of galaxies, each with its own central black hole shaping its destiny. In similar ways, Sagittarius A is simply our closest example, the one whose influence we can feel most intimately. But as we understand how it shaped our galaxy, another question arises. What will happen when this calm balance is disturbed? Because far away, another giant is moving toward us, Andromeda. In a few billion years, their paths will cross and two supermassive black holes will begin to spiral toward one another. Part 9. What will happen when Andromeda collides with us? There is a storm coming. Not tomorrow, not in 1,000 years, but in about 4 billion years. A storm so vast it will reshape the night sky, merge every star we see and fuse two entire galaxies into one. That storm is Andromeda, our nearest spiral neighbor, now moving toward us at a speed of 110 kilometers per second. Right now, it hangs in the northern sky as a faint smudge of light, barely visible to the naked eye. But telescopes reveal its true scale, a disk of stars more than 220,000 light-year across, roughly double the size of our Milky Way. It contains nearly 1 trillion stars, and at its center sits another supermassive black hole called M31*. One day it will meet Sagittarius A*. To understand this cosmic meeting, scientists from NASA, ESA, and the Hubble Space Telescope have spent years tracking the motions of Andromeda's stars using precise astrometric measurements. By combining these observations with computer simulations, they've created a detailed timeline of the upcoming merger. In about 4 billion years, the distance between the Milky Way and Andromeda, currently 2.5 million light-year, will begin to close rapidly. The two galaxies are bound by gravity, and nothing in the expanding universe can stop their collision. The space between them is almost empty, so most stars will never physically collide, but their mutual gravity will tear both galaxies apart and rebuild them into a new form. Astronomers call the future product of this union Milka or Milkdromeda, a giant elliptical galaxy that will shine brighter and rounder than either of its parents. Simulations by the Harvard-Smithsonian Center for Astrophysics show that during the merger, the sky from Earth or whatever replaces it will change dramatically. Over hundreds of millions of years, Andromeda will swell from a faint smear into a vast whirlpool, filling half the heavens with luminous arcs of starlight. Spiral arms will stretch, break, and twist into glowing bridges connecting both galaxies. As the gravitational tides rise, the outer stars will be flung into long streams, ribbons of light hundreds of thousands of light years long. Gas clouds will collide, compress, and ignite bursts of new star formation, creating thousands of brilliant blue stars. For a brief moment in cosmic time, the newborn Milka will be among the most active luminous galaxies in the local universe. Yet beneath this spectacle, a quieter and more inevitable process will be unfolding at the centers of both galaxies, the supermassive black holes. Sagittarius A times and M31 asterisk, will begin their slow mutual approach. At first, each will continue orbiting within its original stellar core, but as gravity stirs the system, dynamical friction will draw them closer together. Every nearby star they pass will lose a little energy, carrying it away like ripples in water, causing the two giants to spiral inward. This dance could last hundreds of millions of years, but its ending is certain. Eventually, the distance between the two black holes will shrink to just a few light years, and that's when something extraordinary happens. At that scale, the motion of the black holes will begin to generate gravitational waves, ripples in spacetime, first predicted by Einstein and directly detected by LIGO. In 2015, these waves will radiate energy away from the binary system, tightening their orbit even further, like a cosmic whirlpool, losing energy to its own gravity. As the two event horizons draw near, they'll accelerate to half the speed of light, curving spacetime so violently that the entire galaxy will briefly tremble in invisible rhythm. When the final merger occurs, it will unleash one of the most powerful events since the Big Bang, a black hole fusion, releasing more energy and gravitational waves than all the stars in the universe emit in light at that moment. The resulting object will likely weigh between 100 million and 200 million times the mass of the Sun, forming a new, ultra-massive core for Milky Way. NASA's upcoming LISA mission, the Laser Interferometer Space Antenna planned for launch in the mid-2030s, is designed to detect the kind of long-wavelength gravitational waves such mergers produce, although the actual Milky Way Andromeda collision will happen long after humanity's time. LISA will observe similar events in distant galaxies, giving us a preview of our cosmic future. ESA describes LISA's goal simply to listen to the universe, not in light, but in gravity. As the two galaxies fuse, the night sky from a distant vantage point would become breathtaking. Stars would stretch into luminous filaments, their orbits distorted by tidal forces. The spiral arms would vanish, replaced by an ellipsoidal glow. Eventually, only a smooth round galaxy would remain, calm, vast, and redder as its youngest stars fade and only older ones remain. Our Sun by then will have changed too. It will be nearing the end of its life, swelling into a red giant and consuming Mercury and Venus. Earth may be long gone, but the Sun's remnant, a white dwarf, will continue orbiting within the merged galaxy, tracing a new path through Milky's core. In that distant era, Sagittarius A asterisk successor will sit quietly, again, surrounded by stars it helped forge. The merging process itself will not destroy the galaxies instantly. It is more like a long gravitational waltz lasting billions of years. After their first encounter, they will pass through each other, stretch apart, and then fall back together again, repeating this process several times before settling. During each passage, massive shock waves will ripple through their interstellar gas, triggering temporary starbursts. Computer simulations from NASA's Goddard Space Flight Center illustrate this beautifully. They show how the Milky Way's spiral arms warp and bend as Andromeda's gravity pulls them out of shape. Blue clusters of young stars ignite along the tidal bridges while older stars drift into vast tidal tails. When the galaxies finally coalesce, their central bulges blend, forming the bright core of a new elliptical galaxy. One might wonder, if galaxies collide, could entire solar systems be destroyed? Surprisingly, the answer is no, at least not by direct impact. The average distance between stars is so enormous that even during the merger, the odds of two stars colliding are astronomically low. However, gravitational perturbations could shift planetary orbits, fling some systems into intergalactic space, and form wandering sunless worlds adrift in the dark. It's a gentle chaos, not a violent one, a reshuffling of cosmic architecture, not its destruction. What will remain constant is gravity's language, silent but absolute. The merging of galaxies, the spiral of black holes, the emission of gravitational waves, all follow equations Einstein wrote over a century ago. And remarkably, modern instruments like LIGO and LISA are still catching up to his predictions, turning his mathematics into sound. When LIGO detected the first black hole merger in 2015, it captured a tiny fraction of the process that will one day happen on a galactic scale. That event involved two stellar mass black holes, only a few dozen times the mass of the Sunday. The future Milky Way-Andromeda merger will repeat the same dance, but with black holes millions of times larger. ESA scientists note the Milky Way-Andromeda collision is the destiny of our local group, a process written in gravity since the dawn of time. After the merger, Milo will slowly fade. Star formation will dwindle as gas is consumed or expelled. The galaxy will grow redder, quieter, and more spherical. The merged black hole at its center will dominate, holding the memory of two great spirals within its gravitational well. And beyond Milky, new collisions will continue. Perhaps in another 10 billion years, it will merge again with the triangulum galaxy M33, creating an even larger elliptical system. The universe never stops rearranging itself. It is a constant builder, sculptor, and recycler of galaxies. NASA scientist Dr. Roland Van Dierel summarized it best. This will be the ultimate fate of the Milky Way, a merger written into its motion since its birth. From our current vantage point, though, there is only quiet anticipation. When we look up at Andromeda tonight, we are seeing it as it was 2.5 million years ago, long before humans existed, long before we had eyes to witness it. Every photon that reaches us carries a message from the past and a glimpse of the future, because that faint glow in our sky is also our cosmic mirror. When two galaxies collide, they do not destroy each other. They evolve into something new, more massive, more stable, a continuation written in gravity's slow language. But as our galaxy's story approaches that distant future, another question begins to rise. After the Milky Way and Andromeda merge, what will the universe itself be evolving toward? Part 10. How will we study it next? We have finally seen the unseeable, the shadow of a black hole. But this is not the end of the story. It is only the beginning of a new era, one where our instruments will not just look at Sagittarius A*, but watch it breathe, flare, and spin in real time. The next generation of astronomy is not about bigger telescopes. It's about smarter ones tuned to the invisible forces that shape space and time. Over the coming decades, new observatories from NASA, ESA, and international teams will open windows into frequencies and polarizations we have never explored before. Each will focus on a single question that remains after all we've seen. What is Sagittarius A actually doing right now? The first piece of that puzzle is already orbiting above us. The James Webb Space Telescope, or JWST, with its 6.5-meter gold-coated mirror and infrared vision, JWST can see through the thick clouds of dust that obscure the galactic center. Its instruments near and detect light at wavelengths between 0.6 and 28 microns, perfectly tuned to trace warm gas and dust near Sagittarius A*. In mid-2023, JWST's early release science programs began capturing the first deep infrared images of the inner Milky Way, revealing newborn stars and filaments of gas twisted by gravity. JWST's sensitivity allows astronomers to monitor infrared flares from Sagittarius A that correspond to reconnection events near its event horizon. Each flare lasts minutes. Yet in that time, the black hole releases more energy than our sun will emit in a century. By measuring the color and timing of these flares, JWST can infer how fast the black hole is spinning, a property still unknown but crucial to understanding its history. Spin in black holes is more than a number. It determines how space-time twists nearby, how magnetic fields align, and whether jets can form. If Sagittarius A spins quickly, it may still store enormous rotational energy, waiting for the right conditions to release it. JWST's precise monitoring, paired with X-ray observatories, will soon reveal that story in exquisite detail. Next comes the quiet revolution of polarimetry, the study of how light waves align as they travel through magnetic fields. In December 2021, NASA launched the Imaging X-ray Polarimetry Explorer, the first mission dedicated to measuring the polarization of cosmic X-rays. IXPE's detectors can tell whether photons from a flare near a black hole were emitted in a straight or twisted field, offering clues about the geometry and turbulence of the plasma. In 2023, IXPE began a series of coordinated observations with Chandra and XMM Newton focusing on Sagittarius A and other low-luminosity active galactic nuclei. By combining these data, astronomers are reconstructing how the direction of polarization changes during a flare, effectively watching the magnetic loops rotate and reconnect. NASA describes this goal simply: turns light into a compass, pointing to the hidden structure of cosmic fields. At the same time, the Event Horizon Telescope, EHT, is preparing for its next generation, a transformation even more ambitious than the first. By 2026, the EHT collaboration aims to add new observatories to its network, extending its reach to Africa, Greenland, and space-based platforms. This will increase its baseline, the distance between telescopes, making the array even sharper than before. It will no longer produce single snapshots, but movies, frame-by-frame sequences, showing how plasma swirls and fades around the event horizon. The new system, often referred to as NGET, Next Generation Event Horizon Telescope, will include real-time data correlation, adaptive calibration, and advanced algorithms that can track the black hole's time variability. With 10 times the sensitivity and frequency coverage of the current array, NGT will image Sagittarius A in multiple wavelengths simultaneously, revealing how magnetic structures evolve and how spin affects the accretion flow. According to Dr. Shepard Dorman, the project's founder, our next goal is to make black hole cinema, to see how the ring flickers, how the plasma moves, and how gravity sculpts time itself. Meanwhile, X-ray astronomy is entering a golden age. ISA's upcoming Athena mission, Advanced Telescope for High-Energy Astrophysics, scheduled for the early 2030s, will bring unprecedented clarity to the high-energy universe. Athena will measure how gas flows in and out of galactic centers, detecting shifts in energy so subtle that they reveal the velocity of matter orbiting black holes in real time. It will complement IXPE and JWST, giving us the full spectrum, from infrared to X-ray, of how Sagittarius A breathes. And then comes a dream long whispered among astronomers: space-based interferometry. If radio dishes on Earth can act as one telescope, imagine what could be done if we placed telescopes in orbit, thousands of kilometers apart, free from atmospheric noise. Such a system could achieve resolution hundreds of times finer than today's EHT. Concepts like millimetron, a Russian, European project, and Event Horizon Imager propose exactly this. Satellites, forming a network in space to directly image black holes in ultraviolet, infrared, and radio bands at once. LISA mission planned for the mid-to-2030s will add yet another dimension: sound. LISA will detect gravitational waves from orbit using 3 spacecraft separated by 2.5 million km connected by laser beams. Unlike ground-based detectors like LIGO, which can only hear short, high-frequency bursts, LISA will listen to the slow, deep vibrations from massive black hole mergers, including events like the eventual fusion of Sagittarius A and M31**. In ESA's own words, LISA will open the gravitational wave sky, letting us hear the universe breathe. When all these observatories, JWST, IXPE, NGT, Athena, and LISA, work together, they will create a multi-messenger of our galactic core. Light, magnetism, and gravity will be read as parts of a single story. We will no longer see just the shadow of Sagittarius A*, but its rhythm, its flicker, its pulse, its spin. Already prototypes of AI-based data pipelines are being tested to handle this flood of information. Machine learning models will sort petabytes of raw data from simultaneous instruments, cross-matching light curves, polarization angles, and gravitational signals. This fusion of human intuition and computational power will help us interpret complex phenomena like magnetic reconnection, jet formation, and the coupling between black hole spin and surrounding plasma. Even now, JWST is providing hints that Sagittarius A may have a faint echo residual energy from a minor flare that occurred just a few centuries ago. By analyzing these faint afterglows, we can trace how material moves through the dense molecular clouds around the galactic center, giving us a sense of how black holes interact with their environment over time. Every one of these missions, from space telescopes to interferometers, is part of a broader shift in astronomy. A move from still images to dynamic observation, from isolated wavelengths to multi-messenger science. This approach lets us see not just what exists, but how it evolves second by second across the entire electromagnetic spectrum. It's remarkable to think that only a century ago, black holes were theoretical curiosities, solutions to equations few believed could exist in reality. Now they are among the best observed objects in the universe, and soon, with the instruments we're building, we will be able to study them, not as static monsters, but as living laboratories of physics, where gravity, magnetism, and light meet in their purest forms. NASA's Dr. Jessica Lu put it this way: Sagittarius A times lets us watch general relativity unfold in real time. The story of our galaxy's heart is no longer written only in equations. It's now visible, audible, and measurable in motion. From the cold detectors of JWST to the laser arms of LISA, every instrument adds another sense, another layer of awareness to the universe we inhabit. And while these missions look outward, they also remind us of something profound in their precision, that the cosmos is knowable, that with patience, mathematics, and cooperation across continents, we can see even the darkest regions of space. In the decades ahead, our telescopes will no longer just observe Sagittarius A*. They will listen to it. They will follow its flares, track its spin, and hear its gravitational whispers as they ripple through space-time. As ESA once described the purpose of these missions, to turn silence into signal and darkness into data. And so, our quiet journey through the center of the galaxy reaches its resting place. From radio attic in 1932 to the glowing shadow in 2022 to the observatories of the future, each step has brought us closer to understanding the most powerful object we can never touch. If this calm exploration has brought you even a moment of wonder or peace, I'm deeply grateful that you've spent it here under the same stars where this story began. The soft tap on like or subscribe is the gentlest way to let me know these night voyages mean something to you. And if you'd like, I would love to know where in the world you're listening from. Perhaps the quiet of midnight or the first light of dawn. Your words and presence keep this small universe alive. So until our next cosmic story, sleep well, dream of galaxies, and remember, even in the deepest dark, the universe is still speaking. Wishing you a peaceful night, a deep sleep, and the sweetest dreams among the stars.